Here we got a positive number. So the index. And it's sort of okay. So let's. So here again is what is the map? The map is x, y, z. Remember this was our parameter. Minus a, I guess, whole square. B square. So this is the torus with the core circle having radius a, and this characterizing circle having radius b, and a is bigger than that. Yeah, but you can again, parameterize it in the obvious way. You learn in the course of curves and surfaces, for example, that you go a distance a along an angle theta, and then you go up along a radii of n b along an angle psi, and then you project everything and get the x, y, z. Same plus b cosine theta, and then b cosine psi. This is the typical parameterization of the torus. In fact, parameterizing the torus globally, except that at theta equal to 0 and pi and psi equal to 0 and pi is equal to over. Otherwise, it's one single sort of square which wraps everything. Anyway, this means I can think of this as theta and psi. These are my two local coordinates. So theta parameterizes. If you're thinking of the torus, theta parameterizes the, like what's the angle as measured from the point of view of the z-axis. So you will have some point on the torus, but if you just project everything down, you will have some angle on the x-y. That's the thing. And the psi means in one of these circles, how far you have to go. That's the psi. So again, you can sort of check here that. So yeah, so you want to choose a point here. The point here corresponds to this angle equal to pi by 2, correct? Because you, no matter which direction you go, at that point you have to move up an angle pi by 2 to actually go to the top. Here it will correspond to the angle minus pi by 2, of course. So points that you are interested in P as psi equal to pi by 2, theta are. Because you need to evaluate at a specific choice of theta and psi. Here we evaluate t equal to 0 because we are interested in the equation. Same thing. So if you compute this, then you can, so the map is equal to b sin, right, or b sin squared theta, I guess, right? No, this is just a height function, no z squared, the usual height function. So then you have to compute the del 2 of this by del theta 2. Which is minus cosine theta. This sum. Sorry. Sorry. So yeah, you look through closely. This theta is the angle which you have to choose. So you have a point here. This is your psi, and this angle here is this angle here is. On the because of the parameter, because you take b cosine theta and then you add that and then project to the next form. So I want to evaluate at pi by 2, so if you differentiate it twice and pi by 2, you see the equation is 1. So the conclusion is, and here, index. This is a fairly simple check, nothing to check on. Index. Which is expected, but it's a computation to justify it. Because you're going to get minus cosine theta, and minus cosine theta at pi by 2 is minus sin theta at pi by 2 is that's the case. That's one, and in the other case. Alright, so this is the second example, which we have already seen, just to put it out there. Are there any questions? So let me give you one more example which is slightly different, but you should really think of this example as a generalization of this one. Okay, so this is a rather grand example, but you could ask, are there functions that I can hook up on S3, S4 and so on, which looks like this. So here you said there's x and y and you're simply putting del squared. So effectively, me write it down rather than saying. Here, this requires these are my n plus 1 coordinates. Sum of squares equals to 1 because this is here in r plus 1. And so technically I should write Fk because for every choice of k between 1 and n I can construct a function. Because all you're going to do is you're going to choose some of the coordinates here, take the square that one. That's the function. Like here we chose s, pick square and set that to your function. Here we're going to do the same. So when I'm going to choose it in some order, so let me say x. So this really should be Fk. So you fix an index k and then for that k you have this one. So F is really like Fk. So for each k you get a. So if you take your k to be n, then you project onto the height xn plus 1 and then you take it square. So in particular, you notice that if n is the usual height function square. Right? Because the height function is not x1 xn plus 1, maps to xn plus 1. So square it. Right? Z. Right? But you could have all sorts of things. So this is the usual. So when I say usual, the height function is typically considered to be projection on the last coordinate. Nothing specific, but that's how it is. Okay. So here, if you think about it, and forget Morse code and everything. This is a non-negative function. So it's sum of squares, but obviously this is bounded by 1 because this is necessarily equal to the entire sum of squares. So it's between 0 and 1. So now the question is what is the global maximum, what is the global minimum? They ideally should be in the critical state, not anything else. So when do you get the global maximum? Well, when this is 1. This is 1, that means your first 1 through k coordinates are same. But that essentially means you're looking at the complementary n plus 1 minus k dimensional Euclidean space. I'm looking at the Euclid sphere there. Whereas if this is 0, this is the global minimum, then the first k coordinates sum squares to 1. That's like a k minus 1 sphere in the first arcade, right R. So I mean, clearly see that there are two such things. I'll use this for k minus 1. It's just a reindexing, okay? Because I want the first thing to be a k sphere. If I set this to be 0, I'm getting x1 square plus x2 square plus xk plus 1 square is 1. And that's a k sphere. I don't want that k minus 1 just for reindexing purposes. Nothing has changed. And this is n minus k minus 1 n. What is this? So this I is for initial, which means it's the initial k sphere living inside your x. Which means this is the k sphere living inside the first k plus 1. By definition, x1, xk plus 1, 0, 0, I mean, you could have pre-indexed everything between zeros, but too much work at this point. What is this f stands for? This, okay, unfortunately, this f is not that f. Then for the final. This is the last n minus k coordinates. And look at the unit sphere. That's precisely what it is. When this is equal to 1. This by definition. 0, 0, 0, x, what you get? these are the last equation state coordinates, and it's the unit sphere there, because this is the global axis. And you can check that there are no other critical points simply by choosing coordinates differentiating. To differentiate, you see in an appropriate coordinate system, you have to drop all of the x. Differentiate it once, you get two exchange. So one of the exchange has to be constant. So you don't have any critical point. This is a critical set. And this is, for the most part, if this is not N0,